Hi there and welcome to this video for Senior Physics on Quantum Mechanics. Now in this unit, or in this video, we're going to explore the initial theories that made up the quantum theory. Now basically there were a lot of scientists that did a lot of study which led us to this point. And this point basically allows us to break down some of the earlier theories which apply for large particles but don't apply for smaller particles. Particles that basically have very small distances between them, are traveling incredibly fast, or basically exist within the world of the atom. Now we do have theories, Newtonian theories, that basically allow us to explain large body motion, and things like cars and people and even down up to the effect of molecules. But there are theories that don't explain what happens within the quantum realm or within the atom, because they do not obey those laws of Newtonian physics. Now there were two theories that emerged. We've got our general relativity, which was set up by Einstein, and then we've also got our ideas of quantum mechanics. And there were lots of arguments around the general relativity and quantum mechanics as to what was being accepted, and what was the evidence that actually stated that quantum mechanics had some validity within the physics world. Now, general relativity, as I spoke to you about, basically describes the motion and behavior of large matter. So it looks at large body interaction, movement, which really were set up by the theories put down by Isaac Newton. However, quantum mechanics looks at the behavior of subatomic particles and how those particles interact and the forces which are generated which cause them to interact within the atom itself. And basically they make up the standard model for particle physics. And from this we were able to ascertain what the atom was really like. Remember, at this stage, from the evidence found by Ernest Rutherford, all we know is that we've got a dense nucleus which is positively charged with some electrons spinning around the outside, and that's about as far as the theory took us. However, quantum mechanics has allowed us to talk about shell structure and the number of electrons which basically exist within and the position of those electrons which exist within the atom. Okay, so let's have a look at some of the theories. Well, we know that quantum theory allows us to explain electromagnetic force, and this is the force which allows us to hold the electrons within the atom. It's the forces which exist between the nucleus and the electron itself. It also allows us to explain the strong nuclear force. Now remember, the strong nuclear force is the force which holds the nucleus together. Note that the proton is positively charged. Because it's positively charged, it means it's going to repel like protons. Obviously we've got neutrons which are have a neutral charge, and they space the positive particles apart. But there must be a strong force still holding the whole nucleus together. What that is, we don't really know, but quantum mechanics allows us to start putting some theories behind what the strong nuclear force is and how it's created. We've also got weak nuclear forces which occur when the strong nuclear force is released, and we get forces which generate and push out particles. This is in the form of radioactive decay, and we look at the concept of things like neutrinos. So basically, one of the pioneers behind quantum mechanics, who gave us the theories and evidence to start the road of quantum mechanics, was Max Planck. He looked at black body radiation, and he basically proposed that the atoms themselves are all made up of specific amounts of energy. Hence, that energy is quantized. A quanta, basically a certain amount, a specific amount of energy which may exist within particles. Now, he did a lot of work with light, and from this he basically ascertained that a certain frequency of light basically would emit a certain amount of energy. So if you think about our white light spectrum and our Roy G. Biv going from red, orange, yellow, green, blue, indigo and violet, each one of those light wavelengths will come off at a specific frequency. He stated that each of those frequencies gave off a specific amount of energy. So from this he produced an equation. E is proportional to F, where the energy present in a particle of light or a frequency of light was directly related to the type of frequency that he had. So from this, it was graphed, and he produced E equals hf, where h is Planck's constant, which is 6.63 times 10 to the negative 34 joules seconds, and this is then multiplied by the frequency of light. From that, using Planck's constant and the frequency of light, we're then able to ascertain what the energy is for each frequency of light that we've got in any form of the electromagnetic spectrum. Now, for this, in 1918, Max Planck received the Nobel Prize for physics for his quantum idea on both light and matter. From this, the light particles were then given this idea of, the light was actually given the idea of being made up of particles, and these particles were called photons. Now, remember, prior to this, it was established that light traveled in waves. Young's experiment with the ripple tank and the idea of the diffraction grating and producing those slits which produce the fringe patterns. All these were put down to show that light was acting as a wave. And now we've got Max Planck stating that light actually exists as a quantized particle or a photon. So you can see the dilemma which was facing scientists at this time. Now, using the wave formula, which basically comes from v equals d over t, or velocity equals distance over time, we were able to get a formula for c equals f lambda. Now remember that frequency is made up of 1 over the time period. Remember, the time period is the time for one wave to move. So if that's the time on v equals d over t, and d is our distance, when we're talking about wavelength, when we're talking about distance on a wave, we're talking about wavelength. So we get v equals wavelength over 1 over t, which equals t equals 1 over f. So from this we get that f then must equal 1 over t. So we can substitute in for t. So we get wavelength equals wavelength divided by 1 over f. So we flip it over, so we get wavelength times f. And the result is that what we get from there is that v equals wavelength lambda times f, but v is the speed, but we're talking about light here, so light will be given the symbol c, which is light speed, which is basically 3 times 10 to the 8. So from this we get c equals f lambda, as we've got an equation there. Then we can substitute that into E equals hf, so that if we make f the subject, we get c is divided by lambda, so we substitute that into f, so we also get an equation which is the energy of a specific frequency or wavelength of light is basically hc over lambda, or the wavelength. So let's look at a little example. Here we're going to calculate the energy of a photon of blue light of wavelength 4 times 10 to the 7 meters. And we know that the speed of light is 3 times 10 to the 8 meters per second. So we know our wavelength, we know our speed of light, and remember we also know Planck's constant, which is 6.63 times 10 to the negative 34. So we substitute that into our equation. We can find our frequency, or we can substitute it in, as I said, in that previous equation, and as a result we end up with 5 times 10 to the negative 19 joules. So in this case we've used our frequency, we've calculated our frequency, we've substituted it into E equals hf, and then we found our answer. However, we could have done E equals hc over f, and just use over lambda, and substituted in 4 times 10 to the negative 7 meters. Either one would work. So I hope you found that useful. That just gives us an overview into our quantum theory. I do hope you'll join me again and looking at quantum theory in a little bit further detail, where we'll probably look at the photoelectric effect. So that will follow on some of the theories that we've got from Max Planck. Do check out other iTunes U courses that have been produced on my website, which is aussiephysics.com. And I hope you've enjoyed this video, and I look forward to you meeting me again. Bye for now.